Alright, so welcome to this video. In this video we're going to look at volumes, but we're going to look at volumes of cross sections. So four shapes that we're going to be looking at. We're going to be looking at some squares, equilateral triangles, some isosceles right triangles, and then finally some semicircles. But in this video I'm going to focus on these two shapes that you see right here, the square and an equilateral triangle. So what I want to do is I want to find the volume. Let's start off with the square. I want to find the volume of this square. Now, to find the volume, we know that the volume is always equal to the area, so the area of our base, so the area of the base, times the height of our shape. Alright, so that's the basic idea for finding volume. Now, if we look at our square, we can say that our square maybe has a height or maybe a depth of, let's call it delta x. So let's call this length right here delta x. Now, because it's a square, we know that the sides are equal. So we know that this side, we'll call it s for side, is the same length as this side right here. So this side right here is the same as this. So what is the area of the base? Now the base is this part right here. So there's our base. So what is the area of the base? Well, the area is just a square, and the area of a square is equal to side times side. So we end up with side times side, or side squared. And then we're going to multiply that by our height. But we said that our height here is the delta x. So delta x. So the volume for a square with some depth of delta x, or with some width, is just s squared times delta x. Now imagine this is just for one single square. Now imagine if I asked you to accumulate infinitely many of these squares. Well, then our formula would become the volume would be equal to the integral, since we're accumulating so many, from a to b, and it would be s squared dx. Now this s, we're going to look at some examples in the next video, but this s right here is going to be the side of the square, so this is going to be something that we're going to have to figure out. I'm going to put a question mark, and I'll explain how we figure out what s is in the next video, or in the upcoming videos. Let's jump over to the equilateral triangle. And again, we're going to use this same idea, so excuse me there. So we're going to use this same idea here, that the volume, let me go ahead and put this in pink, that the volume is equal to the area of the base times the height. Alright, so let's jump over to the equilateral triangle now. Well, again, let's call this s. But if it's an equilateral triangle, that means that all sides are the same. So that means this also has to be s. And let's also add some width to it, some depth. So we're going to say that this width, or this depth, is delta x. So the question now is, so sorry if I cut the video off there, or if it sounds a little awkward at that moment. I'm here in the classroom and an announcement went off. So okay, so back to the equilateral triangle. So a question here is, well, what is the area of the base, right? So if we think about cutting this equilateral triangle in such a way, we need to figure out the area of the base. Now, the area of the base is a triangle, so the area of a triangle, well, what is the area of a triangle? Well, that's just equal to 1/2 the base times the height. The good news is that we know what the base is, right? The base is s, so we know that this guy is just our s, but what we don't know is we don't know what the height of this rectangle is. So we don't know what the height, and I'm going to call this, let me zoom in a little bit. Let me just erase this. Give me 1 second. Alright, so I'm going to call that h. So we don't know what that h is. But I do know the Pythagorean theorem, and I can definitely go ahead and use a Pythagorean theorem to go ahead and solve for h. So let's go ahead and do that. So I know that, let's say that this s squared, so this one right here, so we have s squared, that's the hypotenuse, is equal to, well, it's equal to this side right here, so that's going to be h squared plus, now here's the part you got to watch out for. We're talking about this, let me pick a different color. Let me do this in red. We're talking about this triangle right here. Now what is the bottom, this bottom part right here? Well, that's half of s. Remember, s is the whole side, but we're only talking about a little piece of it. So that's half of s. So we have plus 1/2 s s squared. So let's go ahead and solve this equation for h, and let's see what we get. So we have s squared is equal to h squared plus, let's see, 1 squared is 1, 2 squared is 4, and then we have s squared. I'm going to go ahead and move the 1/4 s squared over, so now I have s squared minus 1/4 s squared, that's equal to h squared. And if I take the square root of both sides, I get that the square root of, well, actually let me do this instead. Before I take the square root, can I combine like terms? So we have s squared minus 1/4 s squared. That turns out to be 3 over 4 s squared equals h squared. So what I can go ahead and do now is take the square root of both sides. We're going to have the square root of 3 s, let me scoot this up a bit, give myself some room, over 2, because the square root of 4 is 2, and that's equal to h. Now I know you might be thinking, well, plus, minus, and all that stuff, but remember we're talking about height here, and height is always positive, so we ignore the negative solution here. So we have it. We have what h equals, right? H is equal to this thing here. So that means I can go back to my formula for the area of a triangle, which is sitting up here, and I can substitute what h is. H is now the square root of 3, the square root of 3 times s over 2. So the area of the triangle, let me go back to orange now, this is going to equal to 1/2 the base, but remember the base is s, and then instead of writing h, I'm now going to write the square root of 3s over 2. Now, that looks very, very ugly, and I can go ahead and actually clean this up. This is actually going to clean up to, let's see, 1 times square root of 3 is square root of 3, 2 times 2 is 4, s times s is s squared. So there you have it. There is the area of our base, which is this part right here. So this part here in orange. Alright, so that's the area of the base. Now I got to multiply that. If I want the volume, I got to multiply it by our dx, right? Our delta x. So it turns out that our final answer here, so our volume here, the volume is going to be equal to square root of 3 over 2 s squared times delta x, right? It's exactly what we have here. We have the area of the base times the height of our shape. Over here we had the area of the base times again the height of our shape. And it's the same thing over and over again. The same idea for these problems here. Now what I want you to remember or to keep in mind is that this one right here, the volume formula that we found, this is just again the volume for one single equilateral triangle. Now if I want to accumulate an infinite amount of equilateral triangles, then I'm going to have to integrate from a to b, and we'll figure out what those limits are. And again, oh, I'm sorry, I think I messed up here. Let's see. Yes, I messed up in my formula. We had a 4 sitting there, and I wrote a 2. So let me go ahead and fix that really quick. So let me erase that. Let me put a 4 here. There you go. That's better. All right. So our formula is now going to become the integral of this thing here. Now, the square root of 3 over 4, that is just a constant, right? So I don't have to write it inside my integral. I'm just going to take it out. So I'm going to write the square root of 3 over 4. Then I'm going to have the integral from a to b, and then I'm going to have s squared dx. And there is my actual formula for volume using equilateral triangles. So I'm just going to put this in a box. So again, I encourage you to replay this video, kind of try and make sense of it a little bit more and how we got these two formulas right here, and maybe try and come up with it on your own as well. In the next video, we'll look at 2 more shapes, and then in the following video after that, we'll finally do some examples using these formulas here.